Welcome to the Worldwide Center of Math. We've been taking a look at some of the basics of probability. One of the things that we just took a look at was calculating the probability of two events occurring at the same time. Now, we looked at conditional probability, which means that we're looking at the probability of an event B occurring given that A occurs. So that's what this notation means. And the probability of B given A is going to be the probability of A and B over the probability of A occurring. Now there is a formula called Bayes' formula that we use to calculate conditional probabilities like this. We're actually not going to take an in-depth look at Bayes' formula today, but it's going to be a really important tool when you are calculating conditional probabilities. And Bayes' formula is this. So we have the probability of B given A. B given A is going to be the probability of A given B times the probability of B. And as we noticed in the last video, that is the probability of A and B. And then it's going to be all over the probability of A happening, which is A given B times B and plus A given not B times not B. So Bayes' formula is going to be really important. I'll write that out for you. When calculating conditional probabilities, Bayes' formula is super important. So we take a look and use conditional probabilities and probabilities in this probability tree here. This is going to be often used to calculate conditional probabilities or used to calculate and probabilities. So basically what we have here is the event A or the event not A occurring. And then after A happens, we have either B or not B, or we have after not A happens, we have B or not B again. So we're taking a look. This is going to be the probability of A on this arm. This is going to be the probability of B given A on this arm. And then you multiply these two and get the probability of A and B. And we see from the probability tree that it's just A times B given A. We could go through the whole tree and take a look. Instead, we're going to take a look at an example. So our example says we have a deck of cards, full deck of cards, normal deck of cards, no jokers. And the card game is won when a player draws two spades. So basically what we have, we're going to start off with one card draw, and we have either spade or not spade. So the S stands for spade, and the SC stands for not spade. So the probability of drawing a spade is 1/4. The probability of not a spade, 1 minus 1/4, or 3/4. Now, we didn't originally state, but the problem states that we're not replacing the cards in the deck. So once we've drawn a card, there are only 51 cards left. So we need to account for that in each of these. So here are your second card possibilities, another spade or not a spade. So if we do draw a spade on the first one, that means there's only 12 spades left in the deck out of 51. So we have a 12 out of 51 chance. This one is a spade and then not a spade, so it's 39 out of 51. This is a spade, not a spade and then a spade, so there's still 13 spades but only 51 cards left. And then not a spade and then not a spade. There are 38 total cards left that aren't a spade out of 51. So now we multiply through and find out the probability of getting a spade and a spade, the probability of getting a spade and not a spade, etc. So we do quarter times 12 out of 51. We can cancel the 4 and do 3 out of 51. Now, in the end, we're going to have a bunch of numbers with the denominator as 204. So we're just going to expand that, and we have 12 out of 204. I'm just going to go ahead through and write out the probabilities for the tree, and we're going to see exactly what we're calculating, spade and not spade, or not spade and spade, or not spade and not spade. Now, as we mentioned in the last video and earlier in this video, these probabilities are actually the same. It's just that they're reversed. So we do see the property that the probability of A and B is equal to the probability of B and A, which is just equal to the conditional probability of one given the other times the probability of the other actually occurring. So these probabilities are going to be 1/4 times 39 over 51 and 3/4 times 13 out of 51, which both end up being 39 out of 204. Now this last probability that we get a not spade and not spade, is going to be just 3 quarters times 38 out of 51, which is 114 out of 204. So all you have to do is some simple addition to see that the probabilities over here add up to 1. 12 plus 39 plus 39 plus 114 comes out to 204. That probability is 1 that we get one of these four, or if we're asking that the probability that we get this or this or this or this, we simply add them all together and the probability is 1 because those are all the possibilities of 2 card draws.
Thank you for watching. For more math videos, please subscribe to our YouTube channel here. Or for additional resources, including affordable digital textbooks, please visit centerofmath.org.